All right, let's have a look at the first question. We are trying to push a crate across a horizontal surface. Initially, the crate is not moving at all, but when we apply a force of 73 newtons, that is just enough to set it in motion. So if we look at the force diagram for such a crate, we will have the weight of the crate acting downwards, and there will be a normal force acting upwards. We need to push with a force of 73 newtons in order to set this crate moving. And that 73 Newton force is opposed by a frictional force acting in the other direction. It might jump out at you that the vertical forces and the horizontal forces must be equal to each other, but we're going to do the step-by-step process to establish that. This process will be useful later on in more complex problems. The F of S stands for force of static friction. This crate is not moving, which is why we have that S there. N is the normal force, and mg is the weight of the box. So if we look at our forces in Y, there is no acceleration, so the net force must equal 0. We then add up our vertical forces. We have a positive N and a negative mg. We put those two lines together to give us 0 equals N minus mg, telling us that N must be equal to mg, which you might well have intuited already. We'll do the same thing for the forces in X. Net force in X is also equal to 0 because we are dealing with the moment before the box starts to move. Applying that 73 Newton force is the force that gets us to the tipping point where it's just about to start sliding but has not yet started to do so. So we add up our forces in X and we have a positive 73 Newton force and minus the F of S force, the static friction force. Putting those two lines together gives us the fact that 0 must be equal to 73 minus the static friction force. So the static friction force must be equal to 73 newtons. That's another bit of information that we're going to be using very shortly. The final piece of this jigsaw is the friction equation that we looked at today, or yesterday as you're looking at this. And that equation tells us that the static friction force is equal to the coefficient of static friction multiplied by the normal force. We're trying to solve for the coefficient, so we'll rearrange it. So it says mu s equals F of S over N. Then it's just a question of, do we know all of the bits that we need in order to calculate that coefficient, that mu s? And we don't know the static friction force as given in the problem, because it's not, nor do we know the normal force. However, the work that we did just a few moments ago told us that the static friction force is equal to 73 and that the normal force is equal to m times g. So we can at this point just substitute in our data and say that the coefficient must be equal to 73 newtons divided by the mass of the crate, which is 23 kilograms, multiplied by 9.8, which is the value of g, 9.8 meters per second squared. Calculate what that is, and that will give us our final answer. There are no units to this final answer because it's a coefficient, and like we said, coefficients do not have units. Okay, the second part is asking us to essentially repeat this process, but now the box is sliding. However, the box is sliding at a constant speed, and that's important because it tells us that there is no acceleration in any dimension for this part of the problem either, which means we're going to end up with some very similar looking math. Our force diagram looks very, very similar too. The only difference being that my horizontal force arrows are a tiny bit smaller than they were before as my force is reduced. I'm going to label them mg and n. This one here is my applied force. This is me pushing with a force of, what is it now, 51 newtons. And instead of labeling this F of S, I'm labeling it F of K because we're now sliding, so this is kinetic friction, not static friction. Our force analysis is going to give us the exact same result. Net force in Y is 0, which leads us to finding out that N is equal to mg. I think we can skip those intermediary steps there. In X, no acceleration. It's moving, yes, but accelerating, no. It's moving at a constant speed. So our force analysis for X, when we add them up, tells us our net force is 51 minus F of K, which tells us that that F of K is going to be equal to 51 newtons. And the final part of the jigsaw, just like it was before, is the friction equation. It's the same equation, but we are expressing it in terms of kinetic instead of static now. So those S's that I had before have become K's. I am once again trying to find the coefficient, so rearrange it. Mu K is Fk over N. And just like before, whilst the question doesn't tell us those values, the work that we did doing a force analysis told us what they are equal to. So mu K must be equal to 51 newtons divided by 23 kilograms multiplied by 9.8 meters per second squared. And that will give us our final answer.